So now we're going to try and update our third-person control, but before we do that, I'm going to give a brief discussion of what I'm trying to do. The approach that I'm taking is not the easiest way to set up a character controller. There are far more straightforward ways of approaching this. However, my interests here are primarily in terms of rigging and in terms of animation. I'm not really a programmer, and I'm not approaching this rig programmatically. It is also easier to convert a rig like this to a more straightforward controls-based approach, where the character is controlled primarily by the script, than it is to convert that type of control set to an animated control set. And that is because an animated control set requires both design in terms of the animation as well as the coding. So we currently set up our animation with motion controls. If I was to view these in the context of the Unity interface, we would currently have my inspector here with the blend controls, and these will be laid out in a rectangle. The layout currently has the walk. It then has the various static turns. Our run animations and the animations for the run turning will all be near the top of this rectangle. We're currently working with a set of animations from one of the older standard asset packs, and this is a very useful set of animations because they work with this kind of animation controller, but they are not perfect and they do come with a number of issues. So for context, we'll have our character here. We'll then have our camera relative to this character, and the character's movement should be moving relative not to the character itself, but relative to the camera. So if we were to look for this from a top-down view, we'd have our camera here. We would have a forward vector for the camera. The player will always be located somewhere in front of this. The player does not always need to be directly in front of the camera, but for the moment that is what I'm going to be doing with this controller. So all of our players' movements are going to be performed relative to the camera, so we can almost consider the rotations to occur on a plane which will rotate with the camera around the center of the player. Another easier option would be to use a fixed camera, where the camera is actually moved relative to the player, and the player and the camera share the same forward vector. Essentially, in this case, the camera would be a child of the player. However, a fixed camera is not what I'm going to be doing, and this will not be working for my setup. There is another common approach which does use root motion. So for example, if we have the camera moving forward here, we'll have the root motion driving the forward motion of the character. However, the rotation of the character will be dealt with programmatically. So we will not be rotating the character with the animation, but we will be moving the character forward with the animation. This does make things a lot easier to deal with in many cases, especially collisions with scene geometry. Typically, the biggest problem with root motion is collisions with scene geometry and overrunning scene geometry, as well as overrunning navmesh geometry. There's a 50-50 chance that we'll use this kind of system, especially with NPCs, as using full root motion on NPCs comes with a lot of difficulties, but that's not something which is particularly relevant now. Generally, this type of system will also use root motion when we have attacks or specialized moves for the character. So for example, if we have an attack here, a basic punch for example, the animation would move forward in space and we'd track the hip position or the position of the root itself. And this would give us the forward momentum of the attack without any foot sliding. So for this kind of setup, we would often use root motion on the walks or the runs, although we could turn root motion off for these as well. We'd make sure that root motion is turned off for the rotations, and then we would mainly use root motion in terms of the attacks and special moves. While this approach can make things a lot easier to deal with in terms of creating gameplay, it is not the approach which I'm currently interested in. So now we'll look at what I'm going to be doing. So currently we would have our screen, and here we will assume we have a neutral camera, and that the camera is facing directly down our Z-axis. We'll then have our controller, and the Y-axis will point into the screen, and the X-axis will give us our horizontal value, and this will essentially run parallel to the screen. So essentially our controls are aligned with the world, and if our camera does not move or is aligned to the world, the controls will be aligned with the camera. So what I want to do instead is convert the input from the controls into a vector, and then transform this vector relative to the player. Once that vector has been transformed, we could use it to drive the animations. So we will have our player here, we'll have the transform space of the player, and we'll have our camera. The forward vector of the camera will always face directly down the screen, although we actually need to convert the forward vector for this to happen, as the forward vector for the camera is not the direction the camera is actually pointing, but the direction the camera is pointing relative to the world. So we'll calculate this forward vector, and then we'll calculate a right vector for the camera. Next, we'll get our information from the stick, and we'll want to get this as a vector. This vector should be placed in the camera space. We can then project the values for this vector onto the space of the player. These projections will give us our vertical magnitude and our horizontal magnitude, and these values will be relative to the character. We will have a slight latency here, in that we'll need to perform the calculation for the camera before we can perform the calculation for the player, so these calculations will have a 1-frame delay. So once again, we'll need to get our control vector. We'll need to move this into the space of our camera, and then I'll need to project this onto our player transform. This will be the basic setup. There are, however, some potential problems that we will need to take note of. So we'll have the animation rotating with the player, along with the player's transforms. However, this will only apply when the character is moving forward. If we want to turn the character around, we will have issues, because our vector will always be 1, but our left and right will go from 1 to -1. So the values can flip if we are facing different directions. Turning the character around is something I'll spend quite a lot of time on in the future, as it is a very big part of an animation system like this. We will want something like this to take character momentum into account, and in this kind of system, character momentum will depend on the animation. In a more mathematical approach to a controller, we could use physics to control the momentum. Here I'll be looking at animation for that. This part of the setup is something which we will deal with later, but it is something to note now. I should also note that this is one of the most difficult character setups to implement, especially if you're a single person and do not have a team. But for somebody who's interested in rigging and animation, this is still the most interesting setup for me to create. This is also a reasonably big programming challenge, as getting all the animations to work correctly with each other can be difficult in terms of programming as well. So now we're going to start working on the actual movement for the player, and we're going to make the character move relative to the camera. Currently, I'm storing information for the camera on the player itself. If I look at the player and I look at the runtime information, we'll see that I'm storing the camera offset and the camera position. We'll need to add some more information here, the first of which will be a forward value for the camera. I will also want a right value for the camera. For the moment, I'll also store these on our player entity. To do this, I'm going to work on our script, and I'm going to start by working on the authoring component for the player. I'll start by duplicating my camera offset component. These will be the camera forward. We will also want a camera right value. Both of these will have a variable called value, and this variable will be a public float 3. These components can then be added to my entity. I'll duplicate the line for the camera target, and we'll add our camera forward and our camera right. That will complete the authoring component. We can now work on the system for the player. The first thing that I'll need to do is create references to these components. I'll duplicate the line where we create the reference for the camera offset. I'll then have a cam forward variable, and I'll have a cam right variable. The cam forward will get the camera forward component, and the cam right will get the camera right component. We'll then update the values on these components at the end of the script. We'll do this with system_API.setComponent. We'll set these on our player entity, and I'll be setting these with my cam forward variable and with my camera right variable. I'm going to calculate these values after the loop. We do not need to do this every single time we update this loop. Even though there is only actually one transform within this loop, this should actually only ever be updated once, so I will not include it as part of a loop. I'll start by calculating a forward value for the camera. So this will be camForward.value. To do this, I'm going to need to actually get the value of our camera rotation, and the camera rotation is currently created within the for loop. In order to store this value, I'm going to create a variable for it at the start of the script. This variable will be called camera rotation, and it will be a float 3. I'll initialize this as a 0 vector. I should also update my position variable. This should use float3.0 instead of vector3.0. Mathematically, there's no difference, but there is a conversion which will happen here, and we do not need to perform this conversion every single frame. The camera rotation will now be stored within this variable. We can now use the camera rotation to set the camera forward. This will be a float 3 value, so we'll set this with a new float 3. For the x value, we'll set this with camera rotation.x. This value will not have any height, so it will be zeroed in y. The z value will be set with camera rotation.z. The camera rotation is the vector in which the camera is facing, so we're flattening this vector out, and this will give us our forward value. However, we want to make sure that this is a unit length vector, so we want to make sure that this is normalized. I'll do this with math.normalize. We can test this value by using debug.drawLine. I'll draw this line from float3.0. So this is going to be a global direction which we're getting from the center of the world. This will be drawn to the position of our camera forward vector with camForward.value. This will be our z-axis for everything that is happening relative to the camera, and because of this, this will have a blue color. We'll get this with color.blue. We're essentially going to generate a transform, and to do this I'm going to get a right value for the camera. Once again, this will be a normalized vector, so I'll use math.normalize. I'll then get this using a cross product. This will be a cross product of the camera forward.value and a unit vector in y. This will be set with a new float 3. This will be 0 in x, 1 in y, and 0 in z. We'll also draw out some debugging for this value. This line will be drawn from our 0 value to our camera right.value vector. This will essentially be the x-axis for the camera, so I'll give this a red color. I can now return to Unity to test, and after we press play we should be able to see an x-axis and a z-axis for the camera. The camera is currently in front of the player, so we actually need to have this x-axis facing the opposite direction. So I'm going to negate the camera forward value. I'll negate this before it is normalized. Because this has been flipped, I'm going to flip the right value as well, so this will now be the cross product of my up vector and the camera forward. We can test again. I now have a z-axis facing the same direction as the camera. The right axis is actually incorrect now, so I'll reverse the order of the cross product again. I can test this, and these values should move relative to the camera, and these should give me a camera space relative to the player. We can now use these values, and the first thing that I want to do is make sure that the animation is not just updating the position, that it's updating the rotation as well. So after I declare my current position, I'm going to declare a variable called current rotation. This will be a quaternion, and it will be set as an identity quaternion. Then, after I've stored my current position, I'll store the current rotation. I'll set this from our transform, so this will be transform.transform.rotation. In the for loop, I can then update the rotation on the entity with our current rotation. So now our animation will be updating both the position and the rotation of the entity. This means that our entity should follow our player animation correctly. We can now work on updating the animation. So first I'm going to want to get my values from the stick, and I want to convert these values into the camera space. So I want these to be relative to the camera forward and the camera right values. Essentially, if we push the stick in y, we want a vector along our forward value, and if we push the stick along the x-axis, we'll want a vector which aligns with the camera right vector. We can then use these two vectors to calculate another vector, which will give us a value that is relative to these two vectors. Essentially, it will give us a rotation based off these vectors. Doing this is actually very straightforward. So I'm going to create a vector, and this will be a float 3, and I'll call this stick direction. We're actually going to get this value by adding our camera forward and our camera right. We're not going to get the direction from the stick itself. Instead, we're going to use the stick directions as multipliers. The camera directions are both normalized, so using the stick direction will give us a value between the maximum of the stick direction and 0. So essentially we're going to be scaling the camera forward direction and the camera right direction. So this will be camera forward.value plus camera right.value. This will give us a vector which lies halfway between these two vectors, and it will be the sum total of their length, so it should have a length of 2. Since we essentially want a normalized vector, we can actually just divide this value by 2. So the direction of the player will actually be created using the camera vectors and not the value from the right stick. What the right stick will do is it will act as a multiplier for these values. And this is far more straightforward than trying to calculate a vector and move it into the space of these vectors. So I'll multiply the forward value by a magnitude. So this will be right stick dot value dot y. For the right value, we'll get the magnitude from right stick dot value dot x. We can now test this value by drawing it. Once again, we'll be doing this with debug.drawLine. We'll be drawing this line from our origin to the stick direction. I'll set the color to be black. We can return to Unity and we can test. We've now got a vector which is moving between the vectors for our camera space. So this is giving me a directional value based off my camera. So I can rotate the camera and I'll maintain the direction in which my stick is pointing. So my input is now being set in terms of the camera rotation, and we should be able to use these to drive our animation. So I now have my transform relative to the camera. We can now apply these transforms to the player. Before I do this, I would like to give a warning. The method which I use here can work, but it is not a good way of doing this. I will replace this in a couple of videos. Over here, I wasn't thinking properly and I forgot to use very basic vector mathematics. And this section is actually only working properly because I made a typo. So this section is actually fundamentally broken, but I will go through this in any case. What I'm going to do here is actually useful in terms of visualizations, but it is not the best way to actually implement the controls. I'm going to comment out the visualizations for the camera. The creation of my stick direction is actually in the wrong place. I should move this to before where I'm updating the animation. Next, I'm going to draw out the player transforms. So this will be debug.drawLine. I'll be getting the vector from the origin, and I want to get this from the origin to my player transform, but I'm not yet currently referencing the player transform. I'll add a reference to this where I'm referencing the right stick and left stick. I'll store this with var player transform, and I'll get the value with system API.getComponent. The component type will be local transform, and I want the transform from my player entity. I can now use this for the visualization. Once again, I'll be performing these at the world origin, so this will be float3.0. I'll get this with my player transform.forward. I'll need a visualization for the right side as well. However, for this, I'll need the player transform.right. For the colors, I'll give the player transform forward a cyan color, and I'll make the right transform magenta. This will allow us to visualize the player transform relative to the world, as well as viewing this relative to the camera, and we can use this for bug testing our transforms. So we've got our player transforms, we've got our camera transforms, and we've got the transform from our controller relative to the camera. So next, I'm going to project the stick controls onto the player controls, and here is where I make my mistake and forget my basic vector mathematics. I do not have to perform a full projection here, which is what I'm going to be doing. What I should actually just be doing is taking a dot product, as all I really need is the length of the projection, and the dot product will give us the length of the projection. I will probably perform these projections at a later date, when I move the visualizations out of the player system into their own system. All of these player visualizations are very useful, and we will want to keep them, but we don't necessarily need them here. This will be a public void and will be called project vector. This function will take two arguments. There'll be a float3u and a float3v. This function should actually have a return value, and this value should be float3. First, I'll get the dot product of the u vector and the v vector. This will be math dot dot. The first argument will be u, and the second argument will be v. This will be divided by the dot product of our u value and our u value. The result of this should then be multiplied by our u value. This will project a vector onto another vector. I can now use this function, and I'll use it after I set up my stick direction. My first projection will be a float 3. I'll call this P1. I'll call the project vector function. The base vector will be set with the player transform.forward. The vector that I'll project onto this will be my stick direction. I'll duplicate this line and I'll create a second projection, and I'll call this P2, and this will project my stick direction onto my player transform.right. I'll then duplicate my horizontal and my vertical values. I'll comment out the first two of these so I can always go back to them if necessary. I can now drive my character with these projections. I will rename them though. I'll rename these to be projection V and projection H. These will be for my vertical projection and my horizontal projection respectively. We can now go to Unity and look at how these will be used. These two vectors will correspond to the vertical axes and the horizontal axes for my blend tree. The vertical value will essentially always be positive, while the horizontal value can be both positive and negative. Essentially, our PV or our vertical projection will give us our y-axis or our vertical, and our PH or horizontal projection will give us our x-axis here. So we can now use these to update our animation, and here we will replace the right stick with our projection horizontal, but we don't actually want the projection here. Instead, we want the length of this vector, and I'll get this with the math.length function. As stated earlier, we should actually just use the dot product of our vectors here. We do not need to bother with the projection. For the vertical, we'll use math.length. Here I'll get the length of my vertical projection with math.length, and the argument will be PV. This is not going to work, but it will give us an idea of what our issues are going to be. So I do now get movement. However, there will be major issues with the movement, and that is because our length will always give us a positive value, and it will not take into account what direction we are getting from our input. Essentially, any negative input will be turned to a positive value. I'm now going to calculate which way the directions are facing, and I'm going to do this with my dot product. As I said before, I should be using the value of this, and I will fix this later, but it is something which slipped my mind entirely when I was recording this. Here I'm purely going to be using this for my direction. I'll have two floats. The first will be called my forward dot product. I'll duplicate this and add our second float, and this will be the right dot product. I'll calculate this with math.dot. In this case, I'm going to get the dot product of my projected vector, so this will be PV, and of my player transform dot forward. This will give us the direction of our projected vector in relation to the forward vector. For the right dot product, we'll use math.dot. This will be the dot product of our PH variable and our player transform.right variable. These will allow us to calculate direction. After this, I'm going to create a float for a horizontal value and a float for a vertical value. For the vertical variable, I'll calculate the length of our vertical projection. Currently, this value only needs to be positive. For the horizontal, we're going to test against the right dot product. So if the right dot product is greater than 0, we'll have the length of our horizontal projection. Otherwise, we'll have the negation of the horizontal projection. The horizontal will now be set by my horizontal variable, and the vertical will be set by my vertical variable. So now I have my basic system working, but I will need to make some adjustments. I'm going to change the order of calculation for my projections. For the horizontal value, I should only be setting this with the horizontal value. I'll also flip the calculation of our horizontal length. I'll test this again. At the moment, I'm just playing around with the settings to see how they feel with different operations. I'm now getting the character controller which is beginning to work correctly, although there is still a lot of tweaking that needs to be done, and I have made a number of small logic errors which I'll need to fix. The next thing that I'm going to do is make a test for my vertical direction. We're only going to set this if this is greater than 0, If it is, we'll set this off the length. Otherwise, we'll have a value of 0. This means that this will not be affected by any negative values, which will remove a bit of noise from the calculations. And this will give me a basic working controller. As stated earlier, I will need to clean this up, and I'll be doing that in a couple of videos' time.